Hello and welcome to the next What the Heck Tagon video. What the heck?
Tagon.
So this will probably be my last video for about a week or so, and that's only if I get to editing it today. Because if I don't get to editing it today, then the last video I did is going to be my only video for about 2 weeks, because tomorrow, on Friday, I am going to Barbados, which is pretty amazing. Can't wait. It's going to be for a week. It's going to be warm. It's going to be amazing. It sure was What the Past Gone. I'm What the Future Gone. I'm about to film the last part of this video because I didn't get to it before I left. And now I'm back. It was lovely. Alright, so today we're going to do a continuation of what we did in the last video, where I showed you how to graph all of the inverse trig functions. I'm going to now show you how to graph all of the hyperbolic functions, the ones that we sort of fell upon at the end of the Euler's formula series, which is not over, but since the last installment of that series. So these are a bit less interesting looking than the trig functions, because at least the trig functions are like periodic, so you can tell what they are basically, but we will do our best. So we derived them from the complex exponential definition of trigonometric functions by sort of applying the angle sum formulae to those trig functions with a complex input, and we were able to get the hyperbolic cosine and the hyperbolic sine to fall out of the math, which is essentially just the complex exponential versions of the cosine and sine with all of the i's taken out, and so it's a purely real function of a purely real variable. Or, well, you can plug in complex numbers, but now the expression is entirely in terms of real things. So I'm going to graph those today. Let's do it. It appears that trusty Cup of Joe left his mark a little bit. And all you have to remember is what the formulas were for the hyperbolic sine and the hyperbolic cosine, usually written SINH of x and COSH of x, with or without parentheses if it's unclear what is or isn't the input of the function. And we were able to show that this was equal to e to the x minus e to the minus x over 2. And this was equal to e to the x plus e to the minus x over 2. That is to say that the hyperbolic cosine is the average of the exponential function and its reciprocal. And the sine function, the hyperbolic sine function, is half the difference of the exponential function and its reciprocal. So they will be very, very close in value on the right side of the graph, because adding the reciprocal of a very, very large number to that very large number is not going to be very, very far away from subtracting the reciprocal of that same very, very large number from that very, very large number. Because if you have a really huge number, its reciprocal is going to be incredibly tiny. And so whether you add or subtract it, that's not going to create much of a difference between those two values. So these two functions, as x gets really, really positive, like really big in the positive direction, these two functions are both going to approach the same value. And so if I was to divide this one by this one, as x gets really big, it will converge to 1, right? Because their values are getting very, very close. Which is to say that when we define the hyperbolic tangent, hyperbolic sine over hyperbolic cosine, that function will go to 1 as x goes to infinity. You can see that the opposite will occur if x is negative, because if x is negative, then this is going to be the really tiny number, and these are going to be the really big numbers, because it's simply e to the negative x, which goes up to the left, because it's the reciprocal function, as opposed to it going up to the right, like e to the x. And so what happens is these are the two dominating terms, but since they have a different sign, their ratio of this to that will simply go to -1 instead. So as x goes to negative infinity, the ratio will go to -1. And we're going to explore all of these little properties, and we're going to graph these functions today. So let's start with just graphing e to the x and e to the minus x. That'll actually probably motivate it more than just talking about it. So that point right there is 0, 1. 0, 1. There's my graph for e to the x. It even goes through 0, 1, and just about 1e. I even tried to do my best there. And simply because this is e to the positive x, its reciprocal will simply be 1 over everything you see here. Well, 1 over 1 is 1, and since all of this is the reciprocal of all of this at every single point with the same absolute value, it's simply just going to be a reflection over the y-axis. You can also see that that's what it has to be because we're plugging in negative x for x, and that always reflects the function over the y-axis. So we're going to see an identical function, but mirrored. And as we just talked about, the hyperbolic cosine is very simply their average. So we know that 1 plus 1 is 2, and then you divide that by the number of things. We added 1 and 1, so that's 2 things. Divide by 2, we get back to 1. Right? So hyperbolic cosine is going to be 1 at 0. Every input is different at that point, right? So the average of these two numbers is going to be less than the exponential function at all times, because the average of two quantities has to be between them. So it's going to be less than that, and since e to the negative x quickly approaches 0, the hyperbolic cosine is essentially going to get closer and closer to half the exponential function, because it's it's almost half just e to the x over 2, because e to the negative x term gets small very, very quickly. So essentially, we can say just about, if we just imagine it always being about half of the exponential function. It's kind of hard to imagine what that would look like, but it essentially looks something like that. And this is not a parabola, and I know it's not too well drawn because that is not well, that's kind of half, and it's very hard to see the vertical lines when it gets very steep very quickly. So this is the hyperbolic cosine of x, and what this actually is two things. It's the shape of the arch in Missouri, in St. Louis, Missouri, and it is the natural way that chains hang, because this is not a parabola, right? The parabola is just a quadratic function. E to the x is a transcendental function. It has a Taylor series with infinitely many terms, and so it's not simply quadratic. Hyperbolic cosine is in terms of exponential function, so it would also have a Taylor series, an infinite series representation. And so this is not a parabola, but it is in fact the way that chains hang, exactly the function that describes the state of least gravitational potential energy for the chain to hang in the way this hangs. And so this shape is sometimes called a catenary, because that's what the shape of hanging chains were called. And it was a couple prominent mathematicians guessed that this was a parabola, which isn't too far off. If you actually look at it very close to the y-axis, it very well approximates a certain parabola with certain parameters. But it's not a parabola. It's just the average of e to the x and its reciprocal. The other one is much similar. Good one, Sam. So the thing we have to remember about the hyperbolic sine is that in the numerator it was e to the x minus e to the negative x. So we might want to ask ourselves, when does that equal 0? Well, it equals 0 when e to the x and e to the minus x are equal to each other, right? Which only occurs at x equals 0, where they both equal 1. So e to the x minus e to the negative x is going to be 0 at this point, because it's 1 minus 1. So it's definitely going to be 0. And remember what I said, sine goes to positive infinity as you move to the right, and negative infinity as you move to the left, because the e to the negative x term is the dominant term here, and e to the positive x term is dominant over here. So the sign matters in that case. But think about it, the e to the negative x term is still going to get very small very quickly on this side, which means that the hyperbolic sine function will also approach e to the x over 2, which means it will approach the hyperbolic cosine. So these functions get very, very close to each other very, very quickly. In fact, they get to be almost the same value, quite quickly. Just got to introduce Joe for a little while, because again, their reciprocal approaches 1 and negative 1 as you go in either direction. But the hyperbolic sine is actually, much like sine, an odd function, and so it's reflective about the origin. And this is again not a cubic graph, right? It is made up of exponential functions in a way that still has an infinite series representation. And so this is not a cubic graph, this is not a quadratic graph. They are truly their own functions. And we will come to find that this will be the y-coordinate, and this will be the x-coordinate of these functions represent those things. when we talk about points on the unit hyperbola as opposed to the unit circle. And so that will be very interesting to talk about. So that's really what they're for. They are each other's derivative. Not really much else to say. I'd like to start constructing the other functions, so I'll just write that this is in fact the hyperbolic sine of x. So the green one is the hyperbolic sine, the red one is the hyperbolic cosine, and the blues are e to the x and e to the negative x. And so now I'm going to go through the reciprocals of these functions, the hyperbolic secant and hyperbolic cosecant. So the hyperbolic secant is actually really, really easy to figure out because we know the hyperbolic cosine starts at 1 in the middle and as an even function, just like the cosine function, it does the same thing on either side of the y-axis, right? I didn't mention that before, but that's the case as well. And it's very easy to show. So what we know is that it's going to be 1 in the middle when we reciprocate it, because 1 over 1 is 1. And because it gets infinitely large quite quickly, exponentially fast, in fact, it will get exponentially small. So it'll do something like this, almost like a bell curve. But I'm not sure that it's the same. I don't really do much probability distribution or anything like that. So it will flatten out quite quickly, and it starts at a peak of 1 and goes out like so. So this is the hyperbolic secant of x, the reciprocal of the hyperbolic cosine, and the hyperbolic cosecant does something similar but has an infinite discontinuity in it because the hyperbolic sine is equal to 0 at x equals 0. Since we're coming in from the positive direction, it's going to come down from positive infinity. And let's see where it might intersect. The hyperbolic, let's see if we can figure this out. So the hyperbolic sine is always less than the hyperbolic cosine, which means that the reciprocal of the hyperbolic sine must always be more in the positive side. It must always be more than the hyperbolic cosine one, right? So it should do this, shouldn't it? It should never cross. That's my guess. Like, that's what it seems like it should be. I'm just going to confirm that. But of course, this is negative down here, so it's going to come from negative infinity, and it's going to approach the x-axis from below. And just like sine being odd, just like hyperbolic sine being odd, the hyperbolic cosecant is also odd, and so it is rotationally reflective about the origin, and just like the hyperbolic cosine being even, the hyperbolic secant is also even. So I'm going to rewrite that so that the hyperbolic cosecant is not in the way, and I will put that there. I'm clearly getting stuff on my green pen. It's annoying. So this one's the hyperbolic secant. Cool. All right, so we've got 2 more to go. That is the hyperbolic tangent and the hyperbolic cotangent. So I just have to switch out the battery now. My sincerest apologies to all 7 of you who are really, really waiting for this video to come out before I went on vacation. Too bad. So we've only got 2 more functions to graph, and that would be the hyperbolic tangent and the hyperbolic cotangent. So I will be drawing the axes first. So this is our x-axis, of course, and this is our y-axis. You can't see that because I'm an idiot. I finally have some quality coffee. As lovely as Barbados was, it's definitely not known for its coffee. Oh, I missed you, Joe. I missed you. Hyperbolic tangent and hyperbolic cotangent. Well, naturally, they are defined in a very similar way that we're used to, in that the hyperbolic tangent is simply the hyperbolic sine divided by the hyperbolic cosine. And so these things will be quite easy to graph. I will do the hyperbolic tangent in green. So we know that it must be 0 at 0 because hyperbolic sine is 0 at 0 and the hyperbolic cosine is 1 at 0. So it will be 0 divided by 1 in the middle, which is 0. As we know from previous graphs that the hyperbolic sine is always on the positive side. It's always less. In fact, in every sense, it's always less than the hyperbolic cosine for real number inputs, and so this graph will always be less than 1 for x greater than 0. But they get closer and closer to each other in value from what we saw in the expressions for the equations that describe the graphs. As x gets really, really large, they start to just look like e to the x over 2, both of them, which means that they approach each other in value, which means the hyperbolic tangent is going to approach 1 rather quickly. And so it's just going to asymptotically approach 1. Since the hyperbolic sine is odd, we're dividing the negative version of what's over here by the same thing on this side for the hyperbolic cosine. So we just end up with another odd function that approaches -1 from the bottom, from the top, and approaches it asymptotically. You'll find that it looks quite a bit like the inverse tangent function, but if you were to scale this up by pi over 2, it will not be the inverse tangent function. As nice as that would be, wouldn't it be great if they were that intimately connected, but they're simply not. So this is the hyperbolic tangent function of x, tan h or tanch or something stupid like that. I'd much rather say the full mouthful than say something positively preposterous like cinch or cosh or tanch or anything like that. Trusty Cup of Joe, why you always leaving marks on my board? You're not very trusty today, even though that mark's been there for a week now. And I will notate it just so it's absolutely clear. These are asymptotes. These are horizontal asymptotes at -1 and 1. Therefore, the hyperbolic cotangent is quite easy to graph as well, because it's simply the reciprocal of this graph. And so we know that it's going to be divergent at x equals 0, and since it's approaching 0 from the negative direction, from below here, we know we're going to be coming up from -infinity, and because it's approaching -1 from above, we know that the hyperbolic cotangent is going to approach -1 from below, because it's simply the reciprocal. And so we have it coming up from the bottom. It will simply just approach 1, -1, like that. And likewise, on the other side of the graph, because we're approaching 0 from the positive direction, from above, we're going to be coming down from positive infinity, and it's just going to approach 1 in the exact same way. And so this is the hyperbolic tangent, then this one is the hyperbolic cotangent. They are reciprocals of each other, which means since this is hyperbolic sine over hyperbolic cosine, this is hyperbolic cosine over hyperbolic sine. And you'll see very clearly that both of these are odd functions. So this is how you graph all 6 of the hyperbolic functions. In the next video, I will be doing the graphs of all the inverse functions. We actually will only need to do like 1 or maybe 2 domain restrictions in the entire thing. So it actually won't be very difficult to figure out how to graph these things, because all that we're going to be doing is reflecting them over the line y equals x. But I think it's relevant to describe what they look like because we want to be familiar with them, because I'm going to have videos involving logarithmic versions of the inverse trig and inverse hyperbolic functions. And then when we're finally done with that, I'm going to do the analogies of these functions with the unit hyperbola that you're familiar with regards to the trig functions and the unit circle. So we'll be getting to that shortly. Those will be the next couple of videos that I do in this series. I may f off and do other things in the meantime, just to really piss off Hal over 9000. Yeah, we'll see where this brings us. And before I end, I just wanna make it very clear. All these functions have nice definitions. So just to be absolutely clear, so we have from Euler's formula that the sine, we'll say sine of theta, is equal to e to the I theta minus e to the negative I theta over 2I. And the analogous function, hyperbolic sine of t, is e to the t minus e to the minus t over 2. So it's essentially the sine function without any i's in it, without any imaginary component. The cosine of theta is equal to e to the I theta plus e to the negative I theta over 2. And the hyperbolic cosine function is simply e to the t plus e to the minus t over 2, right? So these should all be relatively familiar to you, right? They're simply the analogous versions without any complex numbers. Likewise, the hyperbolic cosecant, the regular cosecant of theta, is simply the reciprocal of the sine, right? It's 2I divided by e to the I theta minus e to the negative I theta. Looks very, very strange, but this is perfectly valid definition. And similarly, the hyperbolic cosecant function of t is just that without any i's, right? Because it's the reciprocal of the hyperbolic sine. So it's 2 over e to the t minus e to the negative t. Similarly, the secant function of theta is 2 divided by e to the I theta plus e to the minus I theta, and the hyperbolic secant function of t, just to clearly differentiate between an angle and some parameter t, we have 2 over e to the t plus e to the minus t. And now, of course, we can do the tangent and cotangent versions. So the tangent of theta, which is simply the sine divided by the cosine, is going to give, sine divided by cosine is going to give e to the I theta minus e to the minus I theta over I times e to the I theta plus e to the minus I theta, right? And if we do the hyperbolic tangent of t, we simply get this without any i's, so we get e to the t minus e to the minus t divided by e to the t plus e to the minus t. Right? And of course, the next two functions, the cotangent and hyperbolic cotangent, are simply going to be the reciprocals of these things. So the cotangent of theta is equal to I times e to the I theta plus e to the minus I theta over e to the I theta minus e to the minus I theta. And the hyperbolic cotangent of t is just this without any i's. So it's e to the t plus e to the minus t over e to the t minus e to the minus t. And just to be sure, the I here in the numerator and the denominator is from the I in the denominator of the sine function in exponential form. So that's why there's an I there. You can confirm that for yourself. That's definitely necessary for the definition of the cotangent and tangent functions in their exponential forms. I just thought I'd quickly cover that just to show you that they all are expressible in this exponential way, where the hyperbolic versions of the functions are just those without any of the complex numbers parts in them. And it should also motivate the fact that the inverses of all of these can be written in some sort of logarithmic way, since they're all being expressed in some exponential way, so inverting these functions should provide that. And I hope this video was enjoyable. I'll have one more graphing video for the inverse hyperbolic functions, and then we'll move on to the logarithmic versions of the inverse functions, and then we'll finally get to graphing what they look like with regards to the unit hyperbola, much like the trigonometric functions do with the unit circle, as I did very early on in my YouTube channel. And now that we're at the end of the video, because I didn't edit this at the beginning, I'd very much like to thank Flammable Maths for hosting my little tag-along extra video in his Complex Numbers But Different series. I got many hundreds of subscribers out of it in like a day. It was very, very awesome of him. I really, really hope we can continue to collaborate in the future. He is a real mensch. So thank you very much for watching, and stay tuned for the next quick little thing. This channel has an Instagram, so it is at whatthehectagon, of course, and it has a Twitter also. So this is Instagram, and of course this is Twitter, and it is of course naturally, also what the hectagon, at what the hectagon. Nope, at the hectagon. Oh, can't spell today. Okay, hectagon. And my email is the incorrectly spelled what the hectagon. Why spell check before you make the email, right? That you can't then change, at gmail.com. Now, all of these are in the description if you don't want to have to somehow watch the video and pause it and actually write it down. Along with other Instagram, Twitter, YouTube accounts that me and my friend Bill run. He does one for D&D. We together stream on Mixer under the moniker of Fredwood Live. So check the description for other stuff. This is just for my channel. This is my Instagram, at whatthehectagon, Twitter, at whatthehectagon, and email, at whatthehectagon, because I spelled it wrong when I made the email and now I can't change it. So that's the stuff. Thank you for watching, and bye-bye.